So when it comes to sketching functions, and I know some people might be going, well, why do we even bother doing this anymore? It's 2019. We have calculators. We have Desmos. We have other software. And you're absolutely right. Personally, myself, if I had to graph something, I would get my graphing calculator. I'll get Desmos. But what if your calculator's out of batteries? What if your laptop's across the table and we're even that lazy to get up and get it, and we needed to see the shape of a function? We have to have a way to sketch it by hand. Now, if your function is simple, we have techniques to graph that. What is the simplest function we can think of? Well, this is the function that you guys have been studying since Algebra 1, linear functions. The idea for linear functions of the form y equals mx plus b, those guys are super duper easy to graph because we have special techniques for them. So linear functions of the form y equals mx plus b are easily, and this is probably not an English word, but I'm going to make it an English word, graphable. Oh. Why? Well, equations in this format tell you information. Bless you. The m, of course, is your slope, which tells you your rise over the run, which, of course, tells you how far up and down you go versus how far left and right you go. And the b part is your y-intercept, which, of course, is your starting number on the y-axis, right? So that's why linear equations are very easy to sketch, because the equation itself gives you information. You start with the regular number, and then you listen to your slope. So just for the sake of completeness, we'll do one example, even though sketching a line is probably something that we can all do in our sleep, which some of us are probably doing right now, talking about graphing lines. Say, for example, I ask you to sketch, I don't know, y equals 2/3 x minus 1. The idea being, hey, this equation's in slope-intercept form. It gives me information. The slope of 2/3 tells me I'm going to go up 2 and right 3. And the y-intercept of a minus 1 tells me to start at -1 on the y-axis. So you go ahead and make your Cartesian plane. Oops, wrong color. You make your Cartesian plane. You make your tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you basically read the equation. Oh, my starting value is y equals -1, so I'll put my starting number on y equals -1, and then I'm going to listen to my slope. From this starting point, I'm going to go up to right 3 and make a new point. And if I felt so inclined, I can repeat the process. Up to right 3. Or if I didn't want to go up and to the right, I could reverse directions. Instead of going up and to the right, I can go down 2 and left 3. Right? So either way, you can generate a whole bunch of points, and then, of course, your line. Ooh, I can't draw a line. Of course, and your line is whatever connects them all. Almost perfect. No, it's perfect. There you go. So sketching a line, it's very simple because we have a process, we have a methodology, we have a technique to sketch. Well, of course, the concept is, well, Mr. Vo, what if I don't have a simple function? What if I don't have a simple linear function? This is pre-calculus after all. Well, this is sort of the good news and the bad news, and they're both the same. The bad news is, when your function is more complicated, we really don't have a general technique to handle it. We don't have these tricks and shortcuts. The good news is, we don't have any special tricks or shortcuts. It utilizes the same process. So for any other complicated, and I'm put the word complicated in quotes because it really isn't complicated. For any other complicated function, we can sketch using an XY table. That basically is the only technique mathematicians have when they want to sort of experience a new function they've never seen before. I mean, this is how the ancient Greeks looked at functions. And they didn't have calculators. They didn't have fancy methodologies. No, they just said, gee, I have an equation here. I want to see what it looks like. Let's make an XY table. For example, suppose I ask you to sketch, f of x equals x minus 1 cube. Right. So it's not a line because it has an exponent of 3, and that's a pretty, quote, complicated function. I don't know what it looks like. So if I wanted to graph this guy and I didn't have a calculator or I didn't have Desmos, just turn to a regular XY table, right? Tried and true. It's a method that you've been doing since middle school. We do it every single year because, hey, it works. And in math, if it isn't broken, let's not fix it. A common thing that, for whatever reason, stumps kids when I teach this is, hey, Mr. Vo, how do you know what x value to choose? Well, it doesn't matter. You get to choose whatever x value you want. You want to choose x equals 20? Go ahead. You want to choose x equals 5 million? Go ahead. My advice, my suggestion, since we have to actually sketch this out, choose numbers that are small enough that you can graph it. My usual default is I try to center around 0 and a few going to the positive and a few going to the negative. So I like to stick around, say, -3, -2, -1, 0, and of course the positives, 1, 2, 3. I'm not saying that these numbers will work for every single function, but I say it's a pretty good starting point. Sometimes you need them, sometimes you don't, sometimes you need more. And then to get the y values, we do what we did yesterday. We evaluate. Can I assume that we all know how to substitute and plug stuff in? Yeah. Can I just fast forward to the answer? All right, so I'm not going to show the work. I'm just going to say it out loud. But if you plug in a -3, you should get a -64. Plug in a -2, you get a -27. Plug in a -1, you get a -8. Plug in a 0, you get a -1. Plug in a 1, you get a 0. Plug in a 2, you get a 1. Plug a 3, you get a +8. Now, when it comes to hand sketching, notice I analyze the outputs. Gee, I got -64s, -27s. Those are pretty big in magnitude. I could make my tick marks go every 2 or tick marks go every 3. But since I have lots of small numbers as well, -8, -1, 0, I'm basically going to ignore these two results. And when it comes to sketching, that's sometimes what you got to do. If the outputs are too big, just ignore it. So I have my points. Draw my Cartesian plane. Draw my tick marks. I know I'm going to have at least 8 of them, so let's see if I can fit 8 on either side. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I can. Oh, if I was to do this myself, I'll just get graph paper, and I have graph paper for you in the front there, but for the notes, we'll make our own Cartesian plane. 4, 5, 6, 7, 8. I did not space that out correctly. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And I guess I only needed space to the y's, not the x's. And then you just basically plot points. Again, I'm going to skip this and skip this because, I can't plot -64 and -27. So plotting -1, -8. Plotting 0, -1. 1, 0. 2, 1. 3, 8. And then you just sort of like squint your eyes, do your best guess, imagine what it would look like if everything was connected. I imagine it would look something like that. So there we go. We sketched it. Not too hard. And that's basically the main idea of this topic here. How do we sketch graphs that are maybe scary looking or complicated? There really is no big secret. Just make an XY table. Okie dokie? Now, you have to be careful when it comes to sketching. The problems, they may do something called domain restrictions. So let's take a look at this example. It's going to look like our very first example. I'll make it easy. It'll be a linear function. But they may do something like this. Sketch f of x equals, I don't know, 2x minus 3. And you're probably scoffing, go, ha, I can do this. That's pretty simple. But then they may put something like, -2 less than or equal to 0, less than or equal to x, less than or equal to 1. This thing here is called a domain restriction. And what that means is your final picture cannot go beyond those x values. So if you did something like this, and I wouldn't copy this down because I'm going to erase it. Oh, this is very easy. Blah, blah, blah. Start at -3, 1, 2, 3. Slope of 2, up 2 over 1. Make my line. Go home, be happy. That's technically wrong because this includes all of the possible x values. Whereas this problem says, hey, no, looky here. I only want those x values. So what do you have to do? Well, when you make your xy table, just only use x values within this interval. So if I were to make my xy table, I would do -2, -1, 0, and 1. But since this is a line, and I know lines only needs 2 points, I'm not going to do the full-blown xy table. I'm just going to do -2 and 1. Because I know that once I have these 2 endpoints, since it's a line, you just connect the dots. If it wasn't a line, if it was something more complicated, I would do the full gambit of all the x values. But in this case, we can be lazy and take a shortcut. So plug in a -2, you get a -7. Plug in a 1, you get a -1. Then you go ahead and graph it. It looks like my tick marks, I need to go up to -7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. You know, this app does a lot of things for me. You would think they'd automatically put in tick marks for me. 5, 6, 7. And then you just plot the points. -2, -7. 1, -1. And because those are the extreme... Oh, -1. Thank you. There you go. Since those are the extreme values of my domain restrictions, I know that's it. All you got to do is connect the dots. Right? So that is the graph of that function. And notice I drew a line segment. That is the correct answer. I know it sounds nitpicky, but if you gave me something like this, ooh, that's definitely wrong. If you gave me something like this on the test, that technically is not the right answer because, again, you didn't stay within the domain restrictions. I would have to deduct points there. So that should be the answer. That should be the graph. Okay? Now, as I sort of hinted yesterday, since we're in pre-calculus and you're preparing for future math classes, the only way functions can get hard is if I put multiple pieces in them. In other words, if we have piecewise functions. Sketching piecewise functions utilizes the previous skills that we talked about. The only difference, you might have to do it 2 times, 3 times, 4 times in one problem. But that's the only difference. The skill sets are 100% the same. So suppose I ask you to sketch f of x equals, and this is going to be a piecewise function. Let's say we had, I can't read, -x if x is less than or equal to 0. 5 minus x squared if 0 is less than x, which is less than or equal to 3. And then 2 if x is greater than 3. So this piecewise function looks just like the previous example. No, a function with domain restrictions, but all together, and there's 3 of them. The way I would approach this is the same way, table of values, but I'm going to be very strategic here. So I'm going to ask a very obvious question. This is not a math thing. This is a, are you awake and do you have eyes question. If we take a look at the domain restrictions, all of it, can we agree that 0 and 3 are pretty special numbers? So when I make my table of values, I'm probably going to start there. So just to make sure we're all organized, I'm going to color code things. I'll make the first function blue, the second function yellow, and the third function red. So let's start with the first function, the blue function. So for blue, do you guys agree that the special domain restriction is happening at 0? So I'm going to make my XY table. And I'm going to definitely use 0. Plug 0 in, you're going to get a 0. And that's the only special domain value. Move on to the middle function. For the middle function, if I take a look at the domain restriction, we all agree that 0 and 3 are probably special numbers. So I'm going to do my XY table with 0 and 3. Plug those numbers in. Plug in a 0, you get a 5. Plug in a 3, you get a -4. Right. And then for the last function, for this color here, my domain restriction, 3 is a special number, so I'll use an XY table with 3. And take a look at this function. It's just a number. There's no x's to plug into it, so it's constant. So at x equals 3, I still get a 2. Right. And then, just as before, we're going to go ahead and plot this guy. Give myself some more room here. Hopefully that will fit. Make your tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And I'll continue to color code. Now, when it comes to piecewise functions, you have to pay attention to the inequality. Just as with the previous unit, when we sketched on a number line, we saw that, hey, if your inequality has or equals to that little line underneath it, it'll be a solid circle. If it's missing that, it'll be an open circle. These points follow the same way. So for the blue, notice at 0, he has a little line underneath the inequality. When I make my point, he will be solid. So 0, 0 will be solid. Let's move on to the yellow. Well, at 0, the inequality does not have the line, so the point at 0, I'm going to put open. So that's 0, 5 for the yellow. He will be open. 1, 2, 3, 4, 5. But for the middle function at 3, the inequality has that line underneath it. He will be closed. So for 3, -4, he's going to be closed. 3, -4, he will be closed. All right, so you guys understand when things will be open, when things will be closed? All right, so just look at the inequality. And last but not least, for the red function, for the third function, his point will be open. 3, 2 will be open. Beg your pardon, what was the question? The question was, are they going to be 2 separate lines? Well, we're actually going to have 3 segments because we have 3 pieces. Yep.
Wait, sorry, I got a question.
Question.
Why is the yellow one, how come one of them is open and the other?
The question was, for the yellow one, why is one of them open, one of them closed? Openness or closeness is dependent on the inequality of your domain restriction. So for the yellow function at 0, do you see how his inequality does not have an or equals to? He does not have a line. So the point at 0 has to be open. But at at 3, do you see how the inequality does say or equals to? So the point at 3 will be closed. Make sense?
Yes.
Okay. And then you just go ahead and sketch them. So let's go back to the blue function. Now, do you see how his equation, y equals -x? That's just a line. So sketching lines are easy. I don't have to do a table of values. I just listen to the slope. The slope is -1, and normally negative slope tells you to go down 1 over 1. But if I went down 1 over 1, down 1 over 1, I would be making a graph in this direction. But take a look at your domain restriction. It says x is less than 0. This is the x-axis, the horizontal, left and right. If I want less than 0, which direction should I be going into? The left. So I should not be graphing the blue in the right because the domain restriction says I shouldn't go that way. So you just have to reverse your slope. Instead of going down and to the right, we're going to go up and to the left, up and to the left, up and to the left. That's the part for the blue function. I'm going to move on to the yellow function. Well, I can see that the yellow function is a quadratic, and I'm going to pretend, gee whiz, I don't know what a quadratic looks like. This is not a simple line, so you just go back to a table of values. For the table of values for a non-linear, I would use every single number in that interval. So I'll go ahead and, since it's 0 to 3, I'm going to make sure I use 0, 1, 2, and 3. I already got 0 and 3 there, which means I just need to tack on a 1 and a 2. So just go ahead and plug those numbers in. When I plug in a 1, you get a 4. When I plug in a 2, you get a 1. So then you go ahead and plot those points. 1, 4, 2, 1. And then you just go ahead and connect the dots. Now, this is where I'm going to have to break the fourth wall here. I actually do know what x squared will look like. You guys know this should be a parabola, right? My drawing is sort of crappy and it's very tight. It's going to look like a straight line when you connect the dots, but it really should have sort of a curviness to it, right? So I know the way I've drawn it, it may look like a straight line, but it should have some slight of a bow, some slight of a curve, right? And then last, do the third function. It's a constant function of 2. Y equals 2. What type of line will a constant function make? Y equals 2.
A straight line.
A straight line, which direction? Horizontal. Good. There you go. That, as ugly as it looks, is the piecewise function sketched. Yeah, so. Sketching piecewise function, in summary, not very difficult, not very confusing. There's a lot of organization. Just graph each piece separately. I suggest starting at the domain splits and then working away from there.
So why'd you have to add 1 and 2 for the other one?
So the question was, why did I have to add in the table of values 1 and 2 for the middle function? Only because it wasn't a simple linear function, and I was pretending that I'm a student that didn't know what an x squared looked like. So the idea is, if you had to sketch something that wasn't a simple line, the only way you can sketch it is with a table of values, and I just wanted as many points as possible. Yeah. Any other questions with this example? Lovely. Now, why do we even bother with sketching, right? Aside from, for fun, right? I mean, what's better on a lonely Friday or Saturday night than just breaking out a couple of functions and sketch all the way? Literally anything else. The reason why we sketch is because one of the important things in math is identifying functions, because not all equations, not all relations are functions. So that's sort of a key skill that we need to have, and graphing will help us. So determining if a relation is a function. And there's basically 2 ways to do this. One graphically and one algebraically. Right? Of course, we got to talk about the algebraic way. I mean, that's what you guys spend most of the life with, is studying algebra. We don't study Graphica, we study algebra.
Oh, okay.
So let's do the graphically first. So testing to see if something's a function or not just depends on using the definition. For every single input, there exists exactly one output. What is the implication of that definition graphically? Well, it creates this thing known as the vertical line test. Right. And a vertical line test is sort of a test of exclusions. This is basically the idea. A graph is a function if and only if, IFF stands for if and only if any vertical line through the graph intersects at most once. Now, when it comes to definition, when it comes to tests, me personally, having the definition isn't enough. I need to see what the heck this means. So let's just draw 2 examples, one example and then one non-example. So this will be an example of a function. This will be a non-example or not a function. Right. And I'm bad at making up examples, so I'm just going to draw a squiggly snake here. Technically, that is a function. And I'm going to draw a vertical snake here. There you go. Okay. So this is the vertical line test in action, and it's more of a visual thing. So if you're copying stuff down, I would suggest you pause for a second, just look at the screen, because I'm going to be erasing a lot. This is why the left example is a function. Any vertical line I draw, and the emphasis on any, only intersects once. If I draw this vertical line, it only crosses the black graph once. This vertical line only crosses once. This vertical line, only 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 once. As a matter of fact, you can spend the rest of your life drawing a whole bunch of vertical lines, and you'll find out that any vertical line only crosses once. That is what makes it a function. That validates the fact that it's a function. If you take a look at the right example, if I draw, say, this vertical line, oh no, I've intersected twice. That violates the definition of a function, so that's why the right example is not a function. So having a graph to an equation is very helpful in determining if it is a function because you just employ the vertical line test, which I think is a pretty simple test, yes? It's a question that we want on our assessment because that would be 3 points, yes? Okay. Which of course means there's going to be none. Now, not all things are easily graphable, even with computers and whatnot. Not all things are easily graphable, which is why, number 2, we should probably have algebraic ways of testing. So algebraically. I think that's how you spell algebraically. Recall the definition of a function. Every single x should have only one y. Now, you guys also should recall, we're almost done, guys. Please hang with me for a second. Please recall the definition or the idea that when we're solving an equation, when you take an even root, your result will be plus or minus. What does that have to do with whether or not something's a function? Well, if your equation is not written in the generic y equals form, that means you have to solve for y. And that also means the only way you can get really multiple y values is if you have to take an even root. When will you have to take an even root? Well, if there's an even exponent on y. Put it all together, we have this rule. It doesn't have a fancy name. It's not like the vertical line test where it has its own name, so I'll just write out the idea. If an equation has an even exponent on the y, then y is not a function of x. And just like with the graphical situation, let's take a look at an example and a non-example. Or not non-example. Let's take a look. Function and not function. So, I don't know, say square root of y minus x equals 5, right? That looks like pretty funky. Oh, there's something special on the y. That can't be a function. And let's take a look at, y to the 4th equals x. Okay. So let's take a look at the left example, the function example. Let's prove why this guy is a function. So again, equations are typically y equals stuff. So I'm going to solve for y first. And this is a pretty wimpy example. To solve for y, we'll add the x over. And then to get y by itself, I'd square both sides. So, why is this a function? Well, the definition is for every single input, you get exactly one output. So for whatever, any number you plug in for x, just make up a number on top of your mind.
0.
Well, I heard 1 first, although 0 would be nice. If I were to plug in a single 1 in here, I'd get 1 plus 5 is 6. 6 squared is 36. How many answers did I just come up with? 1. 36 is one number. Hence, this is a function. I inputted one number, 1, and I got one number out, 36. This is a function. Contrast that with the right non-function example. Okay, I want to solve for y. So to solve for y, I got to take the 4th root of both sides. Gives me y equals, hey, I took an even root to solve an equation, so it's going to be plus or minus the 4th root of x. So hopefully in this case we can see whatever number I plug into x, say the number 1, I'm going to get a positive 1 out and a negative 1 out. That's 2 y's for 1 x. That violates the definition of a function, right? So you could, do this work every single time, or the shortcut idea, if y has an even exponent, automatically it is not a function. Okay? Question?
Does that include if you can take out a y? Like,
Does that include if you can factor out a y? Yes. So if you I'll put another non-example, like y to the fourth minus y squared plus 3, that sort of thing.
Mm-hmm.
Yeah, because this is an even exponent, eventually we're going to have to take an even root, which will produce pluses or minuses.
Couldn't you like pull out?
Or like heck, even if you have something like this.
Like just that.
Yeah, you can
Couldn't
do
you
y
pull out-
squared.
Or no, just y, because then you would have all odds.
Y.
So
And then y cubed minus y.
Yeah.
If you were to, yeah, so in this example, say 0, 0. In this example, you would still have to eventually somewhere down the line take an even root, because this will give you one answer, y equals 0 and y equals 1. Well, I mean, heck, this is not even a function because I don't have x's anywhere. Say x here, x here. You're eventually going to have to take an even root because, yes, you do have odd powers here and you have odd powers here, but it's still equivalent to this guy, which, forces you to take an even root. Good question, though. So the shortcut idea, how did I tell if an equation is a function or not? Look at the exponent on the y. Okay? So those are the 3 objectives for 2.2. Number 1, can you sketch regular functions? Which I hope the answer is yes. Table of values, worst case scenario. Number 2, can you sketch piecewise functions? And I hope the answer is yes. It's just doing the previous task, but more than once. And number 3, if I give you a graph or an equation, we should be able to tell whether or not it's a function. So that's it. That is 2.2, utilizing graphs of functions.